So the theorem that we just showed has a name, and it's called the dimension theorem. Let us explore a few consequences of this. Suppose that T is a linear transformation from Rn into Rn, and assume that T is onto. So the range of T is all of Rn, so it's the full space. But we already know the dimension of this, so the dimension of these two objects must be the same. So the rank, which is the dimension of the range of T, is equal to n. But let's look at this equation that we have here. If the rank of T is n, we have as a consequence that the nullity of T must be 0. Okay, so the dimension of the null space of T is equal to 0. So that means that the null space of T is generated by a set with 0 elements. So, well, there's only one set with 0 elements, then the empty set. So that means that this must be that. And once we have this, the null space to be exactly this, that means that the function is 1-to-1, because we're dealing with a linear transformation. Now, something we have to note is that this argument works in reverse. I can start with a function linear that is 1-to-1. I will get as a consequence that the null space is exactly this. I will use this, I will use this, then I will obtain that, and finally demonstrate that T is onto. So being onto and being 1-to-1 for linear transformations of this type is the same thing. So let me just summarize that as a corollary. Let T be a linear transformation from Rn into Rn. Then the following are equivalent. T is onto. T is 1-to-1. But if these two are equivalent, then I can combine them and say T is bijective.